It looks like it's the official time. Welcome back, everyone. So for today's class, we're going over section 5.1, but we also mentioned we have our upcoming exam number 3 that's going to be next Monday when we come back. And just the standard reminders, don't forget to bring a calculator. The TI-30X2S is a pretty good one. TI-30XA will do just fine. It can't be a graphing calculator or anything connects to the internet, so one of those types. And don't forget also, you're allowed a page of notes. So definitely use that to your advantage. I would start working on putting that together early, and your notes only have to be up to section 4.7. So it'll be really kind of the same routine that we've gone through twice already, just the third different time next Monday. Any questions at all, folks, about that upcoming exam? Yeah.
Maybe an hour earlier, do you feel at the baby time?
Oh, that's right. Yeah, it's going to be weird. I forgot all about that. Thanks for reminding me. I kind of hate that messing around with the clock stuff. Yeah, we'll get through it. Now that I know it's going to be a daylight savings day on exam, I'll try to make it up to us somehow. That's a rough time to do an exam. Well, maybe, like you said, an hour earlier, maybe it'll be a little bit better. It kind of depends on who you ask, yeah. Well, other questions so far? Okay, well, let's jump back into section 5.1. Oh, I did want to mention, I did make a revision on the sample exam 3 problems. Typically, when I run this class, I've been making a closed calculator, but I've been open-minded about calculators a little bit more. And so the old solutions I had here sometimes said, but on an exam, you wouldn't have to do a problem like this, or calculators wouldn't be allowed. I fixed one of those comments to show, no, on exam, we have a calculator. And so let me go to where that is. The correction is, it's somewhere. It's in red. I thought I was going to find it a little bit faster. Oh, geez. Where in the world did it go? Sorry, oh, there it is finally. That wasn't the best use of class time, but that's where I took out a comment and just put in an approximation. But I also wanted to be clear, sometimes calculators are just nice because if you get that value, you can decide if it's reasonable or not. So that's my main reason of involving a calculator. If you did leave your answer like that, I would have given that full credit for sure. So definitely solve it as normal. And the calculator is there as a comfort and also as an extra check just to see if answers are reasonable. Sometimes we will have to calculate something like, say, doing the problems up here, we have to do some computations like multiplication thing, multiplying things together, but nothing too major. Well, that's my spiel so far for the announcements today. And another reminder, this homework set is officially due a week from today, which would be next Thursday. But because these problems are not on exam 3, I'll accept it at the extended date that's already put in the next Monday. But let's get started then. We mentioned with section 4.9, we're changing gears. We're going from taking derivatives, the differential calculus, to now in chapter 5, we're taking integrals. So we're dealing with the integral calculus. 4.9 bridges the gap, and here's how the notes start. I forgot to open those notes. Give me one moment. A little bit behind today, but we're getting through it. Here are those notes finally. So in integral calculus, this is the main problem we're trying to solve. For differential calculus, we just wanted to find out how to get a tangent line. We're very interested in the slope. Now we're very interested in this area. So the setting is, we want to find the area of the region S. You can't do that unless it's bounded, it's enclosed, so it's finite in area. And so it's going to lie under the curve, y equals f of x. So think of this as the bound coming up from above to give us finite area. Also, it's going to be bounded to the left by the vertical line segment, x equals a. So it's enclosed here, likewise enclosed here by x equals b. And it's bounded below by the x-axis down below. And so that's our setup for the function. So we want to find the area inside this. And turns out there's a really interesting and kind of crazy trick to this. This is really a preview. Under the right conditions, one of the most important conditions is you have a continuous function on a closed interval from a bracket to b bracket. A continuous function on a closed interval will always obtain a maximum value and a minimum value, an absolute max, absolute min. And also, you can find this area exactly by doing this. The exact area is f of b minus f of a, where f, that's an antiderivative. Let's just write it out in this form. F prime at x equals f of x for all x in that closed interval from a to b. So that's really, really weird. And this is called the fundamental theorem of calculus, part 2. So this is the second part of the fundamental theorem of calculus. It says if your function is continuous on a closed interval, this area that we really want to calculate, it has important physical properties, only ever depended on the right boundary, the left boundary, and finding an antiderivative. That's it. That is really, really kind of remarkable in a way. So it's our goal to make this a little bit more precise, see exactly how it goes. But that's why we needed 4.9 so bad, why we have to have good understanding of all those derivatives, because we can't really get an antiderivative unless we're really good at differentiating in the first place. And so that's kind of the preview for what all this is going for in chapter 5. First thing we're going to do is just see how to calculate the area. Then we'll see how it connects with the fundamental theorem of calculus when our methods get better and better in section 5.2, 5.3. So let's just start by imagining how would you even get this area. Here's one approach. This is kind of a bad approach, but you could go like this. And just calculate that as your area. You've underestimated massively, right? Or you could do this. Calculate this as your area. Huge overestimate this time, right? Or you could just break it up. You could say, start putting down rectangles that go like this. Find the areas of those rectangles, and that would approximate. Probably a little bit better than those silly approaches. And so that's what we're going to try to do. Find the area under this curve, y equals f of x, by partitioning the closed interval from a to b with enough subintervals so that we get rectangles approximating this area. And as a number of those rectangles increase more and more, our estimates are going to become better. Let's give this a try right away just to see how it goes. So here's our first example. It's an applied problem too to make it extra fun. It says here the velocity graph of a car accelerating from rest, so at 0 kilometers per hour is what we're meaning by from rest, to a speed of 120 kilometers an hour over a period of 30 seconds is shown. So time from 0 to 30 seconds, and at 30 seconds it went 120 kilometers per hour. That scale is kind of annoying. Let's see if we can complete it a little bit better. This would be 20, 60, 80, 100, and 120 is up here, just for easier reference when we look at this graph. Next it says, estimate the distance traveled using 6 approximating rectangles at right endpoints. Now, somehow we're going to take a velocity graph like this and find distance. And this is what we know about distance. We did this with the fish problem back in the day, a few sections ago, 4.7. Distance is going to be equal to the rate times time. We definitely have time here, so that fits the bill. Rate is this. It's a velocity graph. That's the rate of speed that we're looking at. And so distance being rate times time, really it's just now an area. The time is going to be a length along this horizontal axis. The rate is going to be a height along the vertical axis. If you can find the area under this curve exactly, here's what the area would look like. You found the actual distance. So that's our goal. Let's start by beginning with this portion right here. We're going to use 6 approximate rectangles at right endpoints. What I would say right away to organize information is immediately n is going to be equal to 6. So we're using 6 rectangles to estimate this, and we want our rectangles to be of equal width each time that we do this. So n equals 6 rectangles of equal width. The width is always going to be by this formula. It'd be a delta x if the variable is x. In this problem, it's going to be delta t. And the formula is going to be b for the upper bound. By upper bound, what we're meaning is that number up here, minus a, the lower bound, that number there, that cuts off area, and divide by number of rectangles n. So we want to say how many approximate rectangles immediately form this equation, and the rectangles are going to look like this. Delta t is b, our graph starts at 30 seconds, minus a, it started at 0 seconds, divide by n, which is 6. So this is just 36 for a width of 5 seconds. And now that we see 5 seconds, there is an incompatibility in this problem. It's kind of unfortunate. Velocity is in kilometers per hour, but the width of my intervals is in seconds. We have a strong unit mismatch. It turns out the easiest way to fix this mismatch down here is we can convert the 5 seconds into hours because we have kilometers per hour. And then the time multiplied by the rate would then be compatible as units go. So let's take our delta t. This is kind of unusual to have to do, but I felt like this is a good application to start with. Delta t is going to be 5 seconds. We're going to multiply this by 1 over 1 hour would contain 60 squared seconds. 60 seconds to the minute for 60 minutes for this all together. Then this becomes 5 over 60 squared, which does reduce. I took a look at this earlier today. This reduces to 1 over 720 hours. Decimal number is just fine as well, but this is going to be easier to write in for our delta t. So 1/720th hours is the 5 seconds, which would have been right here. Does that make sense to folks so far? Okay, so the order of the process is, first, figure out how many rectangles you need. Second, you definitely need to get your delta t. Here we kind of did it twice, and this is the official one with the right unit. Third step, we need to know what our boundary points are. The boundary points that are going to partition off each of those rectangles. They'll have a lower bound and an upper bound, and we can write them in like this. Ordinarily, I would write x naught for the first one, but we can start with t naught, since the variable is t. T naught would just be a in every single problem. A is the lower bound, so it's this value right here at 0. We go to the next partition, t1, and to get to t1, we just start at the last one and add our delta t right here. Oh geez, 1 over 120 hours. You know, we can use seconds for this portion and keep the unit seconds here. So all we need is the time and then the height. But when we multiply, that's when we need this value. So I'll use this right here. T1 is going to be the 5 seconds. So here's T1. The 0 was T naught. At T2, just add another 5 seconds. So we're at 10 seconds. T3 at 15. T4 at 20. And let me see if I can zoom just a touch out. T5 is 25. And finally, T6 equals the 30 seconds. If everything is going according to plan, we're just adding delta x to each new value. Oops, excuse me, delta t. I really like the variable x. It kind of messes me up when it changes. And we should end up right at the end of the boundary, right here. So t naught is a, and t6 should be b as a check. Let's put the rest of them on so we can see them. Here's T3. Here's T4. This is time 5, and this one, because there's an arrow, is time 6. So now we have all the information here. We haven't even sketched rectangles, but now that we have the boundary points, we can do so. So next thing to take a look at is this right here. We're doing this at right endpoints, and so our graph should reflect that. And if we don't get the graph right, the algebra down below is going to look really, really weird. So let me use a special pen for this one. Let's go with, well, to do the job, nothing too strong of a color. So if we're using right endpoints, then the right endpoints are these ones. The trick with this is if it says use right endpoints, you'll use the rightmost endpoint as part of your process, which is up to this. But we exclude the leftmost endpoint, T0. If it said to use left endpoints, we would have been using these ones instead. So the instructions right here are extremely specific to what area we actually get and what we're even going to draw. We'll use both formulas when we go through these notes. Let's start at right endpoints. That means the next thing I would do, I guess we don't need to put a bullet on that or a step, go to T1 at 5. It's right here. We go up to this height specifically. That's the height of the rectangle, the actual function value. Its value, it looks like it's 55. And we're going to estimate the area in from 0 to 5 seconds this way. All you have to do is multiply by the width from here to here. We already have the width. We'll use that when we multiply next. And we need a height, but the function itself supplied the height. That's at about a height 55. So we can calculate that area, but looking at it, that's a pretty big overestimate of that area. For this to be a good approximation, probably 6 rectangles isn't going to do it. Maybe 60 is better. But we're doing this by hand, so the counts are always going to be kind of low so we can get through it. So next, we go to T2 at 10. This goes all the way up until it hits the graph, comes down, that's our next rectangle, and then it's rinse and repeat. At T3, it determines the height, and that determines the estimate. Every one of these are going to be overestimates when we go through this. Kind of tedious to draw, but in a certain sense, it's kind of satisfying to see it work out. Last one here. Then finally at 30, goes up here. It's kind of hard to show that's even an overestimate finally, but that's because the derivative is getting close to 0. It's turning flat. When the derivative is close to 0, you don't need as many rectangles. But when the derivative takes more extreme values, if the slope is large, you probably do need a lot more rectangles in those regions. So far, this is the visualization of what we're about to calculate. And let's take another look. Distance is rate times time. Over here on this rectangle, the rate is 55 kilometers per hour, and the time would be the width, 1/720th of an hour. So we're really using this formula in earnest when we go to calculate that area. So now finally, step 4, we put it all together. We're going to calculate the area and write it out. Any questions at all so far in this process? Okay, so here's what we can write. Well, I said area because that's what it is, but we're calculating the distance traveled. So let's emphasize that. The distance traveled, well, it is the area, so that's another thing that's worthy of emphasizing. We're using 6 approximating rectangles at right endpoints. We're going to later call that R6. R for right endpoints, 6 for 6 approximating rectangles. Then the formula for R6 goes like this. Well, first you can imagine what it should be. All these rectangles is width times height, so it should be delta t times f of, let me change that function. The function is v for velocity. Velocity at time 1. So that's this rectangle here. Then we'll add to it a delta t. times velocity at time 2. That gives us this area. And then just keep on adding these in. Delta t times v of t3. Delta t times velocity at time 4. Delta t times velocity at time 5. Kind of wish this was like 4 rectangles, but here we are. One more to go. Delta t times velocity at t6. So that's a formula if we're thinking of just approximate the rectangles or give the rectangles area normally. That's what you would write down. But then that's a clunky thing to write. And so here's how it's typically going to be written. Factor delta t out of everything and write it this way. Then it's going to be velocity at time 1. We might as well put that in. Time 1, we'll think of it as 5 seconds, but we know that that's really 107.20 hours. So velocity at 5 plus velocity at 10, velocity at 15, velocity at 20, plus velocity at 25, plus velocity at 30. Oh, I forgot to print this is. I think it kind of fits. So that altogether is just a simplification of what's above. Next thing we can do is just plug in the information. Now, because delta t is multiplying a velocity in kilometers per hour, this is the point where I would use 1 over 720 to make units compatible. So 1/720th would go here. Let me move this thing out of the way. It never seems to want to stay out of our way, but this is the portion of the problem where we're just going to estimate. So the velocity at time 1, or 5 seconds, here, let's eyeball it. Looks like 55, 56. I'll go with the 55. That's in units of kilometers per hour, multiplying hours. So we're just getting kilometers when we do this multiplication. So we truly are getting distance like expected. Then we go to the next thing. Velocity at 10 seconds, go up to the graph. That one looks like it's exactly 80 kilometers per hour. Plus, now over here, we're at 15 seconds. That one looks like it's 100. Over to 20 seconds. Now it's getting a little harder to tell. I guess 115 maybe. Moving over to here, at that location, it might be more like 118 or something. But finally, they told us that it did achieve a speed of 120 kilometers per hour at time 30 seconds. So we can go 120 right here. So now it's finally all on paper. This is the point in time where I would mention, if this was on your exam, I would give full credit just for this line, because that's the right expression just about to go into a calculator. But it's still a good idea to calculate these. If you skipped it on an exam, I'd say you're prioritizing your time. It might be a good strategy. But on homework, we should get a value out. So let's get a really fast calculator. I forget, Microsoft doesn't know what Desmos is. We have to go to a browser first. And we can just type this in one line. So it's 1/720th multiplying 55 plus 80 plus 100 plus 115 plus 118 plus 120. Let me expand that. Let's just see if it looks right. 6 values is definitely what I would check there. And it looks like, rounding to say maybe the nearest hundredth, this person did a distance of 0.82 kilometers in just those 30 seconds. 0.82 kilometers. So that we did it, folks. This is kind of a weird problem, right? We have a velocity graph. It's kind of hard to imagine why you would have a velocity graph, but not know your odometer reading, distance traveled. But if that happens to you, if your odometer breaks, just take a video capture of your speedometer, and we can decide how far you went. Seems logical, right? If you know your speed, you should know your distance. It's just an area. But a lot of things are areas. It could be energy, it could be distance, it could be something else from physics, chemistry, and so on. Areas have tons of physical properties, just like a tangent line might. So this has suddenly become a really, really important problem. And we'll try it again. Let's mention here that all of these areas that we just calculated came out to, ooh, don't do that though, let me Control Z that. It came out to 0.82 kilometers, but it was an overestimate, right? We overestimated on every rectangle. It just got less bad as we moved on. So let's just mention here, this is an overestimate. So that's finding areas the hard way. And what this should probably feel like is what we are literally doing is no different than what we did up here. This stuff of finding velocities, average velocities, as the time gets smaller and smaller, this is like calculating a derivative from scratch in a really, really slow and painful way. That's pretty much what we just did right here. We found an integral of a velocity curve over that time interval, but in a very slow and painful way, doing it from first principles. And the only way this estimate improves is if the number of rectangles n goes off to infinity. If this is really a continuous function, then as n goes to infinity, the area we will get down here will become the exact area. It becomes the definition of area in a sense. Well, any questions, folks, with the remainder of this problem? Okay, well, let's try it again. If you can estimate with right endpoints, you can do it with left endpoints. And sometimes people do both estimates, average them, because oftentimes one of is an overestimate and the other is an underestimate. But what we'll do on this next problem is we'll just do the left endpoint rule. It says estimate the area under the graph of f of x equals cosine x from x equals 0 to x equals pi over 2 using 4 approximating rectangles at left endpoints. So right from here, this tells us how we're going to calculate. We will use n equals 4 and estimate with, now if it said right endpoints, we would have said R4. But if it's left endpoints, we're estimating the area using L4 instead. Then we'll decide if it's an under or over estimate. So that's how I'd probably start the problem. Look at how many rectangles and what kind of estimate we're making. Next thing to take a look at is the function and the range that we're going to take on that function. Let's plot that and see how this all goes on this problem right here. So one thing that's always going to be just fine is you could just use Desmos to get your plot and then just do a freehand sketch on your paper. Doesn't have to be perfect, and use that as your graph. If you're using technology, you can just use a screen grab right off of here if you'd like, and that'd be fine as well. But cosine is not too bad. We can do that by freehand without Desmos. It goes like this. So here's our x-axis. At pi over 2 is when it's supposed to end. It starts at 0, so 0 is the a value, pi over 2 is the b value for lower and upper bound. The maximum in this range is going to be 1, and cosine starts right at a 1. So we'll go like this. That just decreases down in a smooth, continuous way. Right at pi over 2, it takes on value 0. So we want this exact area. This is y equals cosine x. And next thing we'll do is, to get that area, we have to know how to partition the x-axis. So next step, let's write out our delta x, this time x because the variable is x. Formula is b minus a divided by n, and that's a consistent formula. Whether we're using L4 for left endpoints or R4 or something else, delta x is always the same value here. Then plugging in, b is pi over 2, minus the value a is 0 from right over here. All this is divided by 4, so this is now pi over 2 divided by 4, or 1/4 times pi over 2, giving us a pi over 8 altogether. So the width of all of our rectangles is going to be exactly pi over 8, only because we're going to that specific range and dividing it in 4. So let's build this up. There's going to be cuts that go about like that. The first one is x naught, which is referring to a, which is 0. So that's our first point. Next one is x1, and all we do here is we just add delta x to get to the next point. So this one's pi over 8. X2 is 2 pi over 8. And your call if you want to simplify that. Sometimes when you're placing values on the horizontal axis, it's not a bad call just to leave it in this form. I'll go with that route. I'm going to be a little bit lazy. I'm going to leave them unsimplified just to make the pattern a little bit more apparent. X3, add a delta X, which is pi over 8. You're now at 3 pi over 8. X4, that should be our last one. Sorry, question first? But this one right here would be the fraction we're dividing by, and then that would be the reciprocal, yes. Sorry, I did write that out in kind of a weird way at this time. Sorry about the confusion on this one. Other questions so far? Okay, so our X4, we're adding pi over 8 again, so now we have 4 pi over 8. But because we are using 4 values, 4 pi over 8 should simplify to pi over 2. Looks like it does, so we're in luck here. We've got the right values. So back over here, this is going to be pi over 8 that we found. This is 2 pi over 8, or pi over 4 if you prefer. And this is 3 pi over 8. So that's our setup so far. Next thing we want to look at is the type of estimate. This one is at left endpoints. That is very tricky for sure, so let's be careful with that. If they're talking about left endpoints, my immediate thought would be is we have to involve the leftmost endpoint, x naught, right at 0. But we can only use 4 points, so that's a decent way to think about this one. So these are the left endpoints. Just to compare, if they asked for right endpoints, we'd have used this set instead, the last 4, because then we're involving the rightmost endpoint, x4, which is pi over 2 from here. So if you're not sure which values to use, we're going to do all the methods in the homework assignment and these notes. And you can always turn back up to these to see which ones did we really use. At right endpoints, we use the far right set and we leave off the leftmost one. And at left endpoints, we use the far left set and leave off the rightmost one. Does that make sense to folks so far? Okay, well, now that we've got them, we need to put in our rectangles. And this one is kind of weird. The first rectangle starts at x naught. Now, if we're doing this at left endpoints, we have to put in a height right at this. So we go up until we hit the curve, goes all the way up to here, moves over to the right until we get to pi over 8, and that's our first rectangle. I guess that one doesn't look too weird, but I think it will eventually. Then at pi over 8, we go up, hit this curve, move over to the right. It's a little bit more apparent this time. These are overestimates. There's a little bit more area on the outer edge of all these rectangles. Then we'll do it again at 2 pi over 8. We go over here, move up till you hit the curve, and where you hit the curve dictates the height. So this one is at a reduced height. Oh, that looks just funny. We go over here, come down. All the rectangles are supposed to be of equal width, but keep in mind it's just kind of hard to draw some of these. And finally, at 3 pi over 8, it comes over to the right and then drops down. So this last one, where the derivative became a little bit larger, now it becomes a massive overestimate right around here. Any questions, folks, on drawing those? Yeah. Absolutely. And in fact, that's such an important process that when you do this, take L4, the one we're about to do here, and R4, and divide by 2. This has a name. It's called the trapezoid rule. So that's definitely a great process on these kinds of problems. For our book, though, the trapezoid rule, it turns out it comes up in Calculus 2. That's really kind of weird. So in Calculus 2, we look at the trapezoid rule. And Calculus 1, we just kind of look at left endpoint, right endpoint, and we just stop right there. But you're absolutely right. The trapezoid rule is superior to both L4 and R4. They'll compromise with over and underestimates in a really strong way. But Calculus 2 does a lot of other things. There's Simpson's rule, where you're using polynomials to interpolate and approximate things. But so far we're doing left, right, and midpoint rule. But it's good to know that there's other methods out there that can improve things even more. Well, any other questions so far, folks, with these estimates at the moment? Okay, well, we have everything put down. All we need to do is write out the process. We're trying to calculate an area. That's our end goal. It's going to be approximately equal to this estimate with L4. So area is approximately L4. The formula for L4 looks almost identical to the formula for R4 or R6. We take our delta X, multiply it into a group where we put in the function values. So it'll be f of x naught. Don't forget, we have to start with the lower end. We're only putting in 4 values if it's a n equals 4 approximating rectangles. So f of x1, f of x2, plus f of x3 is as far as we can go on this. So that's going to give us our 4 rectangle heights, and those are just the heights we put here. Next, we plug in the values and throw it all into a calculator. So let's put in delta x. Delta x came from right here, and it's a value of pi/8. Then it's multiplying into a bracket. Now we're just putting in the function values. F is referring to cosine. X naught is referring to 0. So we're doing cosine 0 to start. That's not too bad. That evaluates to 1. Then go down the line. Cosine pi/8 is the next one. And you could calculate that, but that one's no fun. 2 pi/8 is really pi/4. So that one is calculatable. I'll write it as 2 pi/8 just to connect the notes better. And last one, this is also a nasty one to do. Cosine 3 pi/8. But although some of these trig functions are pretty hard to calculate, you could calculate them exactly. That's not our goal. We're still just estimating them, right? So whatever you put in here, it just gets dropped into a calculator anyways. So we're now ready to give an estimate. The rounding on this, I'd say just round it to anything that seems sensible. We could go to the nearest tenth on that one. I'd say that's appropriate. If this was on your exam, I want to just reiterate, I do give full credit to that since that is the right area. All that's left is to calculate it. And here's how I would probably calculate it if it was homework. I would probably just define the function. Where is it? It's cosine, but let's take a look at it. Define that function first. F of x equals cosine x. So there it is. We definitely have a cosine function. Then on the next line down below here, it's not hard to type all that into a calculator, but it's really, really tedious. And any tedium can add an extra chance of making a mistake. So instead, we can put it in this way. Go pi/8, parenthesis, and go f0. That's the same as cosine 0, then plus f at pi/8, plus f at 2 pi/8, plus f at 3 pi/8. And you can probably make this faster with a good use of copying and pasting. For example, kind of go like this. Oh, geez, don't do that. So plus, and then 3 pi/8. Then plus, and finally, here's the 4 pi. Oh, I went too far, didn't I? That's 1, 2, 3, 4, one too many. Don't go too far like that. So we should end right here. The area is 1.183. Well, not exactly, but that's what the left endpoint rule with 4 approximating rectangles would give us. Let's go for 1.18, or 1.2 if you go for that is just fine as well. So that's our area. It's asking if it's an over or underestimate. That's kind of the purpose of the graph, to see everything in action. And from this rectangle alone, we have a pretty big overestimate. Let's say this is an overestimate. But we'll come back to these notes. We have the actual curve cosine x. That means you can form the antiderivative of this curve, take an upper bound of pi over 2, a lower bound of 0, and you can plug it into this information. That will give you the exact area. It's really kind of weird in a way. Just for fun, let's see if we can illustrate that right here. Think of this as purely just a preview, so we'll use a pen that reflects that. If f of x is cosine x, let's get an antiderivative. I would see what the antiderivative of cosine x ought to be. Definitely, if you differentiate sine x, you get to cosine, so we have an antiderivative. This time, I'm not putting in an arbitrary constant because any antiderivative is going to work for this. Let me see if we set any. Not exactly, but f could be any antiderivative. So I'm picking the simplest one. That's what we'll in fact do. Then we'll take f of b minus f of a. That's going to be sine, that's our uppercase f of x function. B is at pi over 2. That's a low effort pi. Let me try better on that one. My sine at a, which is 0. Sine at pi over 2 is exactly 1. Sine at 0 is 0. And this turns out to be the exact area. In a really weird way, an antiderivative and just knowledge of your right endpoint, left endpoint, that's all it really takes. So it took a lot of effort to discover this. That's why they're calling it a fundamental theorem. And that's our end goal. We're trying to see how the process builds together, much like how we built the derivative from scratch, culminating in the definition of the derivative. That's what we're trying to do with these notes, see how it all really works. Because if we never see the pictures and we're just looking at this, suddenly it just seems like a bunch of Greek. There's no connection on why it even works. Well, any questions, folks, with getting through this one? Well, you could add pretty much anything, but if you did add a plus c, here's what this portion is going to go. I'm glad you asked that question. This is a pretty interesting result here. When you go to do the f of b, you would have a sine x, or excuse me, a sine pi over 2, plus c, and then you go minus in your f of a, and here's where the mathematical miracle essentially occurs. This is sine of 0 plus c. The negative sign distributes. It wipes out that arbitrary constant, whatever it would have happened to be. And so this means you can just take the simplest antiderivative, let that constant be 0, because it turns out it doesn't even matter in this process. Every antiderivative will give you 1 as the exact area in a strange, strange way. Does that make sense for that question there? Awesome. Other questions so far? Okay, well, we've got one more to give a try, and let's see, about 24 minutes. That should be plenty of time. Let's see how this next one goes. It's part B, pretty much asking us to do the same thing. This will be our last problem for this set of notes, but I just want to show also, in case we run out of time, there is more notes, but this information is really just connecting what we've been doing, giving a formal definition to things like Rn and Ln, and mentioning, if you want the exact area, the number of approximating rectangles n has to increase to infinity. So we're taking the limit as the number of rectangles increases without bound. That limit is hard to write. It's really long format. And so this portion right here, the repeated addition of those things, is captured right here in the summation notation. So that's all the notes right here is really trying to signify how summation notation is just taking these things, repeat addition, and writing it down in a very, very compact way. We'll do that to each one of these formulas just so we can write them down more quickly. But again, these notes are just connecting from 5.1 to 5.2. The major thing we have to finish off with the homework is this one right here. Our graph is f of x equals 1 over 1 plus x squared. That does have an antiderivative as well. It would have been the arctangent or tangent inverse function. We're estimating the area from -2 to +1 using 4 approximating rectangles, this time at midpoints. Much like the trapezoid rule gives a gives a compromise between over and under estimates. So does the midpoint rule. But the midpoint rule is a little bit harder to write down, so it has that side effect. Trapezoid rule is really, really fast. Nonetheless, let's give this a try. It says sketch the graph in the rectangles. So for the graph, again, you could go and cite Desmos, or you could just do some basic graph by going like this. Give an x-coordinate, a y-coordinate, where y is 1 over 1 plus x squared. We would definitely want to start at, say, -2. And if we plug -2 inside this, it's going to be 1 over 1 plus a 4 here, where we square that -2. So a 1/5, or 0.2 if you prefer. Let's plug in 0 next. That seems like the next decent point to get. At 0, you're just going to get a 1 over 1. Your x squared is gone. So it's 1 over 1 plus 0 for a value of 1 altogether. And I guess we can go all the way to 1 right here. At the right endpoint, 1, it's going to be 1 divided by 2, essentially. 1 over 1 plus 1 squared, which is still 1. So 1/2, or 0.5. So we have a pair of coordinates. Now we can graph that thing really, really fast. Citing Desmos is just fine as well. And you can use screen grabs if you'd like, but that's not necessary. And finally, here's what our graph is going to look like. Let me put it more around here. All of our values are positive, so we can focus on quadrants 1, quadrants 2. We can call this -1, so -2 here, +1 here. And the maximum value we obtained is +1. So I'm going to make the vertical scale be a little bit more stretched out to get a decent picture. We have a point way up here, a point of about 0.2 at -2, and about exactly 0.5 at +1. So our curve should look something like this. It's not the normal distribution, but it almost has that shape. So it looks kind of familiar when you start to sketch it. We want to find the area under that graph. So this here is finally y equals f of x, that whole curve in. I really wish I put that in blue. Let me see if I can trace it out. That's probably better just to do a do-over. Okay, so that's our setup so far. Now we have to find the midpoints. To get the midpoints, first we find the ordinary points. The leftmost point is x0 at -2. And we need to put all of these down. Oh, and that reminds me then, I did skip a step. Let's return to this in a moment. I can't really get all the points in a reliable way unless I know the gap from one point to the next, which is going to be the width of the rectangle. So the thing I forgot is delta x. Let's maybe squeeze it in right here. Definitely don't forget this thing. This is like the superstar of the whole process. It tells us where all the interesting points are going to be located at. It's always b minus a divided by n. And so we'll be using, for b, the upper value of 1. For a, the lower value of -2, all the way here to the left. It asks for just 4 rectangles is what is set up above. So that's our n equals 4. So this is altogether 3/4. The fractions are just fine for these problems, but if you notice it's a nice decimal, no repeats or anything like that, sometimes the decimals are a little bit faster to get through. So for me personally, I'll take the 3/4 and put it in as a 0.75. If it was like 0.75432, then the fraction's probably better instead of writing down all the decimal values. Now that we have that, we can give our coordinates. x0 is once again -2, like we said. Then x1, we get to that value by just adding delta x, and same for every value repeatedly. So this will be a -1.25. x2, add delta x again, and this will be a -0.5. -0.5 plus +0.75 takes us to +0.25. And this is the moment of truth. This is the last one, so it had better be 1 exactly. Looks like we're in good shape. Add 0.75 to 0.25, and we get the 1 that we are expecting. So now that we have all these values, we need to put them on the graph. And that means this value here is a little bit awkward. Let me take off that tick mark. It's no longer relevant to the graph at all. Oh, but the axis is. That is really hard to erase. Let me try a little bit harder. Microsoft is not the best environment for digital ink, but it's just cheap and available. So the actual values we want are these ones right here. So we have -2 and then a -1.25. Oh boy, that's kind of hard to see. Here's -1, so -1.25 should be right here. Next one is at -0.5. So this would be -1. -0.5 ought to be here. It doesn't have to be perfect. It's just organizing the information, but it should look believable or else it just feels wrong. So -0.5 here. The last value we need to put down is 0.25. So if that's 1 over there, about here is 0.25. So we now have x0, x1, x2, x3, and x4 all settled on the graph. But the problem now is we are not using a left endpoint rule nor a right endpoint rule. We're using midpoints this time. So here's a strategy. You can get your midpoints just by averaging each one of these pair of points. You can literally go into Desmos and take a -2 minus 1.25 divide by 2, and that's your first midpoint. But this is a tedious computation. What I want to show you is another slightly faster way to get through this. When I go to calculate midpoints, I usually go in this route. X bar 1 will always be x0 plus delta x divide by 2, no matter what. And that's because it's saying, go to x0, that's right here. Don't go the full distance of delta x, go midway. So delta x over 2 takes you right to that midpoint. And that's a little bit faster to start us off. I still need a calculator, so it's going to be, oh geez, but not in full screen. It's going to be -2. Just trying to figure out where to put this thing. Sorry, just struggling. There doesn't seem to be very many good spots to put this in. Okay, so -2, that's our x0 value right here. Plus the delta x is 0.75, then divided by 2, and that's the same figure that we got from before, -1.625. Then the next thing we do is we take x bar 2, and we're going to continue to add delta x. So the thought on this part is, if you found the first midpoint, it's right here, -1.625, add the full delta x, it'll take you to the next midpoint. So in the calculator, I probably would just go like this, plus 0.75 times 1. We've added another delta x. We went from this location, -1.625, to here, -0.875. And looking at those values, that looks about right. Yeah, go ahead.
And then just choose like 3, 4, 5, 6.
You're saying like around here on this one?
So like in the back.
Right over here?
Yeah.
Well, if you change, say, this one right here, you're saying like putting in ×2 or a 3?
Like in the back.
Gotcha. Yeah, that should work, but you have to keep in mind that it's also been divided by 2. So if you go this route, that ought to work, yes. Here I'm pretty much just taking what we already put in to get the first one, then adding the 0.75. Sorry, 0.75 to get us to the second one. And then I'm just going to copy your strategy and go ×2 to the third, 3 to the fourth. So either way, it should work. But if you put it up here, you have to put in the right multiplication to counteract the 2 as well. But yeah, I think that's a great thought for these. If we go ×1, then that's what we're doing right here. We're adding just 1 delta x, -0.875. Then it's rinse and repeat. If we want to get to the next one, add delta x again, so it's a 2. It'd be a -0.125. Let's double check the graph. If I can kind of fit this in there. We would be at, oh, I should record this first. X bar 3 came out as negative 0.125. Now let's take a look. It would be over here, negative 0.125. That seems about right. It's pretty close to 0. So it's midway between that boundary and that boundary. Then last one, X bar 4. Go back up here and just increment by one more. And here's the last one, 0.625. Let's double check. 0.625 should be about here. And that does look right numerically. If you don't like these kinds of tricks, that's also okay because, again, you could just take 0.25 and a 1, add them together, divide by 2, you get the same result. So averaging by pairs will always work. Going this route is just slightly faster, so it doesn't gain a lot, but if you do midpoints rules a lot, you might like it going this way. Phew, so we have the midpoints. Now we're about ready to sketch the graph. Any questions at all so far, folks? Okay, so the graph here, let's get a color that's going to show up really well. It's a little bit tricky. I need to write down a line from here, a line that goes up right here, but the height of those lines is determined itself by the midpoint. Our first one is the negative 1.625. We put a point right here, that's the function height, then go left and right to complete the rest of that rectangle. So notice right away with that very first rectangle, let me zoom in on that, it definitely compromised. Where the red dot is overestimated area. Over here, that's underestimated area. They don't cancel out perfectly, but they are compromising really well, much like the trapezoid rule would have. So that's the beauty of the midpoint rule. It's not fun to set up, but once it's set up, it does an extremely good job all of a sudden in getting a very accurate numerical answer. Even at just 4 rectangles, it does a great job. So our next one, that's 0.875 here. So what you would want to do on your paper is put your finger about where the red dot is, go directly up, hit the graph, and then carry on your next rectangle through in this way. We really had to use these points to show the extent of this rectangle. So that's why we needed the negative 0.5, negative 1.25. The next one, it's a negative 0.125. So about here, that means we're going all the way up to the top. Put down a little bar, and this goes all the way up, comes through, and connects with this one at the 0.25. And finally, last one is at 0.625. So you would go here on paper, go directly above to this location, connect in this way for your last rectangle. So we did it, folks. That's our 4 approximated rectangles at midpoints. Only last thing to do is calculate the whole thing. Any questions at all, folks, up to get to this stage? Okay, so our end answer is going to look like this. Area is going to be well approximated by the midpoint rule at 4 rectangles. We say M to indicate midpoint rule, and the subscript of 4 to say how many midpoint or rectangles we're using. Formula becomes delta x, and then we multiply it by f of not x0, x1, x3, and x4. We need this height, and that height came from the very first midpoint. So this will be f at, let's go like this just to make it a formula first, x bar 1, f at x bar 2, f at x bar 3, and then f at x bar 4. So that's what it would look like by formula. Now we need to plug in information. We need to remind ourselves what was f of x. That's easy to forget when you're this far along. So let's take that as a screen grab. We also have our midpoints right here. They're also on the, well, no, they're not on the graph. We never drew them in. They've been too busy, I think, is why we didn't do that. But we have them right there. So we'll import them and write this out as, first, look up your delta x value. It came through as a 0.75. Then we need to look up the original function f right down here in blue and the first midpoint, which is negative 1.625. And it comes together like this. It's kind of awful looking because the function is not as simple to write. It is 1 over 1 plus x bar 1 squared. So negative 1.625 squared. So that's our first one. Let me try to improve my penmanship as I go up this. Then we're moving down to this next one. It's rinse and repeat. We're just changing the value that goes inside there. So plus 1 over 1 plus negative 0.875 squared. Now move down, do the same to this one. 1 over 1 plus negative 0.125 squared. They're all squared, so you don't necessarily have to put in the negative sign, but that's a dangerous step to get into. So usually I put it in directly no matter what. But if you're trying to save space, that could help. Then plus 1 over 1 plus 0.625 quantity 2, or power 2 rather. So that all has to go into a calculator. This gives you full credit on an exam already. So if you're short on time on exam, I'd say skip putting it into the calculator and work on the other problems. Putting this into the calculator is only so you can come back up here and see if the answer even looks reasonable. If I get like 10,000, I'm way off. But if I get 0.002, that's going to look bad as well. So now we're at the step, throw it all into a calculator. We could use Desmos again, but let's try a more standard looking calculator just for folks who might be using a TI-83 or something like that. So in one of these calculators, here's how it comes in finally. Once I find a spot to put the calculator, first start by putting 0.75, a parenthesis, and now we're working inside the bracket, which is playing the role of a parenthesis now. So it's 1 divide by, we need another parenthesis, 1 plus, a new parenthesis, negative 1.625, close that parenthesis and square the result. So that's this first term here. And rinse and repeat, it's kind of tedious, but it'll get in there eventually. Plus 1 divided by 1 plus negative 0.875. Now quantity squared on that one. And oh boy, let me look at this. Okay, so that parenthesis closes right here. To me, this is the challenge with this problem is matching your parentheses. So I think we are okay here. Let's do it again. This is probably not the most riveting mathematical material we've ever done in class, but if calculator is part of what you would do in the homework, it's good to show it at least once. 1 plus negative 0.125, square that thing, close parenthesis for that fraction. And last one, 1 divide by 1 plus 0.625. I guess I didn't need parentheses for this one. I'm not trying to capture the negative sign, but we've got it. I close that parenthesis. Now that parenthesis goes along with the bracket. And the hope is it's all correct, but it's kind of hard to tell unless you scroll a whole bunch. Let's take a really quick gander. I feel okay about it. So let's pull enter, and here's what it says it should be. A 0.12. Let me double check my cheat sheet on this one. I did calculate this out just in case there's a calculator problem. And I got a 1.91. I feel like I messed up somewhere on this. It's kind of hard to see where though. Let's take a quick look. So I'm on the far end, right end point. Negative 1.25 squared. The way this scrolls is definitely not super helpful, but there's a mistake in there somewhere. Anyone happen to spot it? Let me go to the right once more. And 16.25. Oh, I said 1 plus. That should have been a 1 No, I'm on the wrong spot of that. I think that was right. I had 1 divided by 1 plus. That was the right sign there. You know, this is a pretty tricky calculator. I got the wrong answer twice. Let's see if we can reconvene with Desmos just to finish it off. Does that sound all right to folks? Okay, one last try. F of x, define that first as 1 over 1 plus x squared. Once you have your f of x function defined, this is way, way easier. 0.75, parenthesis, f at, I'm just going to mention the actual value, the x input, negative 1.625, f at negative 0.875, f at negative 1.125, f at 0.625. That's the answer I was expecting on this one, and it always amazes me. It's so much harder if you're just typing it out line by line like this on a calculator. I messed up something somewhere, probably a sign or a parenthesis. If you define the function first, it's way, way easier here just to get a fast numerical answer. So 1.91 is what I would round this one to. It would come out as pretty much the same.
Okay, about 1.914.
One point,
One point nine oh.
and on Desmos, I got 1.908. That is really weird. They should come out to the exact same value. So one small thing somewhere in your calculator might be just a little bit off. But just like me, that's a hard thing to find. Other questions so far? Okay, yeah, go ahead.
The actual, the graph exercise is greater than or equal to 0. Well, if you can't be below or.
Oh, gotcha, yeah.
Yeah.
You know, it's for the moment only a temporary restriction, but here's what they're referring to. If we're thinking about area, these are nice pictures, but if it ever goes like this, then the same computations that we just took are going to be really interesting, because imagine partitioning this off into a bunch of rectangles. These contributions are positive areas, but when you go down here, you're getting negative areas. We will in fact do these kinds of integral, well, these are really very low effort rectangles, but I think you get the idea. These are all negative areas. And so we're going to get a net area if your function goes above and below. And the real integral that we'll be doing in section 5.3, 5.4 takes into account these pictures right here. Our areas are going to turn into net areas. But for the moment in this section, they only want to talk about area itself. They didn't want to get into areas suddenly becoming negative when it dips below the x-axis. So that's the only reason they're insisting on a positive function. We'll take that off really pretty shortly, actually, in our notes. You betcha. Other questions so far? Okay, well, have a great night, folks. When we come back on Monday, we'll get through our 3rd exam. And then on Wednesday's class, we'll just continue with this information here. Thank you.
I'm curious if you can find that calculator error.
Oh, let me take a look. It's definitely tough.
I think I have it.
Did you find it?
No, I can't find that,
Oh, I
but
gotcha.
I feel like I put in all the answers.
Let me take a look.
So I think it's a 40.
I think it's really
Oh,
just the
625.
2. Yeah,
Right.
there's a missing 2. That's why you're so close on that one. Just something small.
Yeah, and then I started that again and I'm still doing it wrong.
Let me take a look. So you've got 2x. Here you differentiate x, so negative 4y. Here you differentiate y, so x dy dx. Your
Okay,
product
there we
rule
go.
looks good. Oh, awesome. And here 2y dy dx. So I like your derivative. That looks great.
Okay.
And then the next steps are going to be solving dy dx. It's in 2 spots.
Mm-hmm.
So you want to eliminate the 4y and the 2x. Subtract it, add it. That looks great.
Mm-hmm.
Factor dy dx. divide by x plus 2y. And that right there should be your answer.
Is it?
Yeah.
Okay, it's like simplified weird in the book then.
Let me take a look at what they put in.
Like, this is.
From what I saw, it looks like the right answer.
This is assignment 5.
Gotcha. So 5 and
And it's 3.55.
awesome. Thanks.
That's exercises.
Oh, 3.0. Yeah. 3.55 solutions. 2y
wait, no,
minus
that-
x
Yeah.
and y minus 2x. I see what you mean. There seems to be like a mismatch.
Yeah.
Let's see, x squared minus 4xy plus y squared equals 4. What in the world did we miss here? So 2x.
It's
This-
rewritten on this line.
Oh, gotcha. So that to that is the same.
Yeah.
Gotcha. So negative 4y. Then, oh, I think the issue is right here.
Oh, it's
The
supposed to
negative
be a
4 would
Y.
carry into that location still. So this negative 4, when you do a
Mhm.
product rule, it carries down here, but it would also emerge right there.
So it's negative 4y plus negative 4x dy dx?
Yes, exactly.
Okay.
I think that's what was causing the weirdness in your answer.
Okay,
Algebra looked terrific though. It's just that one little spot that I could find.
so it's just this right here?
Yeah, that negative 4, it's gonna
Okay.
change the algebra, but you're gonna be on the right track now.
Okay, thank you.
Questions, Jake, or over here? Sorry, I lost track. Okay.
Go first. I just wanna see.
I am working on 51 and I am trying to set this numerator of the first derivative to 0, and I get to here, and I'm wondering if you could help me get R, capital R by itself.
Yeah,
or
absolutely.
if you see a mistake on my derivative.
Let me take a look. So the original function is,
That one?
oh, gotcha. So differentiating this, the variable is uppercase R.
Yep, and everything else is constants.
So when you go to take the derivative of this numerator right here, it would still be an e squared in that location. Because if you're differentiating
Oh.
e squared, the e squared is like your constant.
Okay, mistake number 1. So would this be okay before I turned it in? Cause I was looking over it again and again. I think I'd like, it's the least scratch.
Yeah, this one's kind of nasty.
Yeah, no, you're good.
So e squared looks good. R
Okay,
plus
good.
R squared minus
No, correct. Okay, I don't know. I
2
kinda-
squared. So you would have an e squared R.
Okay.
Derivative of this would cause a 2 to come down, R plus R power 1 times 1, but that's not
gone.
going to change it. Yeah.
Yeah,
So this looks pretty good.
okay,
Now here's the major trick on simplifying this.
okay. Cause
What
right
it-
here it can just,
When it goes from power 2,
uh-huh,
it's truly just power 3 down below.
really?
And so you can go, oh, you've kind of done the work. This cancels with this right here, reducing that to power 3.
Yeah,
But you could have also went cancel here, write that in as a 3,
okay,
and write that in as a 1. You could cancel just right at that step, but you did the factoring. That's even better. So it cancels here to here. Now you're setting this all equal to 0.
yeah,
And let's
I don't
see,
know,
R plus R minus 2R equals 0 would mean this one you're looking for
yeah.
any issues on the denominator.
Hmm.
But right here, when you go to solve this one would have a solution.
Okay,
You're solving for your uppercase R. And so you could write it in as like a negative R plus R equals
like,
0
where's the pencil?
and solve it for that R right there.
Okay. Cause I just kinda went for it at some point. I was like, you know what, if I get it wrong, I get it wrong and I move.
Right, yeah. These single problems are not huge stakes at all, yeah.
Yeah, no, I'm so done with it.
Question over here, Jake?
Just, I don't understand much of this.
Which one you're looking at?
Like, I have a general idea for this one, but I'm not quite sure how.
Yeah, this
Zero
one
was
is getting
critical
through
on that.
taking the first derivative. test
You
on this.
did?
Yes.
You want to differentiate using that.
I'm gonna cry. I'm just kidding. Just kidding, never
One
mind.
line, parentheses, because it's thing minus parentheses.
Oh, never mind.
And then parentheses.
Oh, okay, girl, you scared me.
Yeah, so that's gonna be your first step on this, is differentiating that way.
Yeah, okay.
And then you have to set it equal to 0 and solve that thing for the critical number.
That'll take a while,
It's a pretty tough problem, yeah.
especially when there's two letters now, because that K is gonna make everything much more difficult.
Right, K is a constant, so your solution that you're going for is gonna be for a variable n. You will need a value for n in this problem. And this one is really, really similar to over here in the notes. Well, I guess we can stop the recording. We're forgetting to do that today.
Oh, yeah.